In January 2025, scientists published proof that had been frozen inside Arctic ice for over 2,000 years. 3 cores drilled from deep within the polar sheet contained a year-by-year chemical record of Earth's atmosphere, and within it, an unmistakable surge of lead that rises and falls in lockstep with the Roman Empire. The ice preserved what Rome's own historians never fully understood: that the empire's mines, smelters, and even its wine were lacing daily life with a neurotoxin, and the Romans drinking the most were the ones holding power. Joe McConnell and his team at the Desert Research Institute set out to answer a question that stretched across continents and millennia. Could the fallout from Roman lead use still be measured today, far from the ruins of empire? To find out, they selected 3 sites across the Arctic, each chosen for its ability to capture the chemical fingerprint of ancient air. The first core, drilled from the central Greenland ice sheet at 71.3 degrees north and 42.65 degrees west, reached a depth of 3,400 meters, nearly the full thickness of the ice sheet. This site offered the longest, most uninterrupted annual record in the Northern Hemisphere, preserving a frozen timeline that spans back over 2,000 years. The second site, on Svalbard's Lomonosov Plateau at 78.02 degrees north and 15.65 degrees east, yielded a 2,450-meter core. Its exposed position along the North Atlantic ensured that winds carrying dust and pollution from Europe and the Mediterranean would be trapped in the annual snowfall. The third core came from the Moscow Peninsula in the central Siberian Arctic, where a 1,850-meter column of ice was extracted from the permafrost region's wedge complexes. Each core was drilled using a stainless steel barrel and a double-wash fluid system, designed to eliminate contamination and preserve the purity of trace metal signals. The logistics of retrieving these samples were daunting. Each site required years of planning, specialized equipment, and teams willing to work in some of the harshest conditions on Earth. But the payoff was a set of cores that together could cross-check and validate every spike and dip in the chemical record. By comparing 3 distinct locations, McConnell's group could rule out local anomalies, confirming that any lead signal rising out of the ice was not an isolated event, but something that swept across the entire Arctic. The choice of sites was not random. Air masses flowing from the Mediterranean and Western Europe regularly pass over Greenland and Svalbard before settling in the polar snow. By sampling both the central plateau and the outer reaches, the team ensured that emissions from Roman mining and smelting, especially those tied to the empire's industrial heartlands, would be captured. The Siberian site, meanwhile, provided a check on whether lead pollution was truly global or more regionally confined. The deepest of these, the Greenland core, became the anchor for the chronology, with every annual layer stacked atop the next, preserving a record that would soon reveal a story Rome itself never told. A single ice core, once sliced open in the laboratory, reveals a mesmerizing sequence, alternating bands of opaque and clear ice, each marking a single year's snowfall. McConnell's team relies on this natural ledger, counting layer by layer, cross-checking each band against chemical cycles, dust, volcanic ash, and seasonal ions to assign a precise date to every centimeter. For the Roman period, the Greenland core offers a chronology with an uncertainty of less than 6 years, a resolution unmatched in any other climate archive of this age. The lead measurements, performed using sector field inductively coupled plasma mass spectrometry in a cleanroom, return values at the edge of detection, showing fractions of a part per trillion. Yet the results are unambiguous. As the timeline advances from 500 BCE toward the first centuries of the Common Era, a quiet baseline holds steady, punctuated only by the occasional volcanic event. Then, beginning around 150 BCE, the numbers begin to climb. By the start of the 1st century CE, the lead concentration surges, rising more than 30-fold above the earlier background. The peak, sharply defined and unmistakable, stretches from roughly 50 CE to 150 CE before falling away just as suddenly. This pattern repeats itself in the Svalbard and Siberian cores, each displaying the same annual banding, the same spike, the same decline. Cross-validation between sites rules out local contamination or errors in dating. Instead, the evidence points to a continent-wide event, one that left its mark on the atmosphere year after year. The annual resolution means that each lead spike can be matched to a specific decade, sometimes even to a single year, allowing researchers to compare the ice record directly with known events from Roman history. McConnell, reviewing the data, describes this as a chemical fingerprint, one that is both global in reach and precise in timing. The sharpness of the Roman lead peak, its synchronicity across thousands of kilometers, and its alignment with the empire's industrial zenith present a puzzle. What could have driven such a dramatic, coordinated rise in atmospheric lead? The answer at this stage remains hidden within the layers, waiting for the next piece of evidence to surface. Caligula, writing in the 1st century Common Era, describes grape must simmering in kettles of copper or lead, thickening into the sweet syrup Romans called defrutum or sapa. He warns that lead kettles require constant stirring to prevent bitterness, a sign that too much lead has seeped into the syrup. Cato the Elder, a century earlier, also recommends lead cauldrons for their steady heat, but tells cooks to taste for a metallic tang and discard any batch that seems off. Vitruvius, the architect, prefers vessels cast from a blend of lead and copper, noting that the alloy resists corrosion and spreads heat evenly. Yet he cautions against storing syrup in these pots for more than a season, fearing the slow buildup of lead. Pliny the Elder records that the Senate once banned sapa made in pure lead pots from public banquets, after it was linked to a condition they called the white disease, likely anemia caused by chronic lead poisoning. These ancient instructions are echoed in the archaeological record. At Pompeii, dozens of kitchen kettles, ladles, and amphorae have been unearthed, their metal composition matching the recipes. X-ray fluorescence analysis shows these vessels were typically cast from an alloy of 85 to 92% lead, with copper making up the rest. In the Casa del Cavatore, one kettle still held a dark residue, which testing revealed to contain lead at levels far higher than found in vessels used for water or oil. Similar cookware has been found at Herculaneum and rural estates across southern Italy, confirming that lead-copper kettles were not a local oddity, but a staple of Roman kitchens. Roman authors acknowledged the risks, but the practical benefits, thermal stability, durability, and a distinctive flavor, kept these kettles in use. The alignment between text and artifact is clear. Boiling grape must in lead alloy kettles was a standard Roman practice woven into daily life. In a modern laboratory, the centuries-old recipe for sapa is recreated with precision, stripping away the uncertainties of ancient kitchens. Chemists begin with fresh grape must, mirroring the harvests described by Caligula, and pour it into a replica kettle cast to match the alloy composition found in Pompeii, 85% lead and 15% copper. The vessel is set over controlled heat, and the must simmers for hours, just as Roman agronomists prescribed. Periodically, samples are drawn and analyzed using inductively coupled plasma mass spectrometry, known as ICP-MS, the same technology Joe McConnell's team used to measure lead in Arctic ice. The results are stark. As the syrup thickens, lead concentrations climb rapidly. Measurements fall between 240 and 1,000 milligrams per liter, levels that far exceed any modern food safety threshold. For context, the United States Environmental Protection Agency action level for lead in drinking water is 0.015 milligrams per liter. Even the lowest sapa readings are more than 15,000 times that limit, but the numbers alone do not capture the scale of exposure. Roman culinary texts and archaeological residue suggest that sapa was added to wine and food by the teaspoon, about 5 milliliters per cup. A single serving of sapa-sweetened wine prepared this way could deliver between 1 and 5 milligrams of lead. For elite Romans, who drank multiple cups each day, the cumulative intake could reach several milligrams daily, enough by modern toxicological standards to cause chronic poisoning over time. These laboratory findings transform the warnings of Pliny, Cato, and Caligula from anecdote into quantifiable risk. The lead content measured in recreated sapa matches the dose models used in the PNAS study to estimate blood lead levels and cognitive outcomes for ancient populations. What began as a culinary tradition became a vector for mass exposure, and the numbers generated in the lab now provide the hard evidence needed to connect Roman practice with the chemical signature locked in Arctic ice. Bruce Lanphier, one of the world's leading experts on lead toxicology, has spent decades tracing the invisible toll of chronic exposure. His research underpins the models used by the January 2025 PNAS study to translate Roman lead intake into measurable health effects. The science is direct. Every microgram of lead added to the bloodstream leaves a mark, especially in the developing brain. Lanphier's analysis of modern data shows that for each 1 microgram per deciliter increase in blood lead, a child's IQ drops by about half a point. There is no safe threshold. Damage begins at the lowest levels. The PNAS team applied this model to the Roman world. Drawing on experimental reconstructions and ancient sources, they estimated that elite Romans consuming sapa sweetened wine would have absorbed between 1 and 5 milligrams of lead daily. Modern biokinetic equations, like those in the IEU-BK and the adult lead kinetic models, show that a steady intake of 1 milligram per day raises adult blood lead by about 0.5 micrograms per deciliter. At the upper end of documented Roman consumption, this translates to an average increase of 2.4 micrograms per deciliter, enough to produce a 2.5 to 3-point loss in mean IQ across the population, especially among children. These numbers are not abstract. They are grounded in dose response curves, validated by decades of epidemiological study. The same equations used to set modern safety standards now allow scientists to reconstruct the health burden of ancient societies. The figures from the PNAS study, 2.4 micrograms per deciliter and a 2.5 to 3-point loss in IQ, are not just statistical artifacts. They represent a measurable, population-wide impact rooted in the daily habits of Rome's wealthiest citizens and preserved in the chemistry of Arctic ice. Lanphier's work anchors this story in biology, not just in history. The Roman lead spike seen in the ice is more than a geological marker. It is a record of cognitive loss on a scale rarely matched in human history. Jerome Neriagu, a chemist and medical historian, set out to answer a question that had haunted both classicists and toxicologists. Could the ailments and behaviors described in the biographies of Roman emperors be traced to chronic lead poisoning? In a landmark New England Journal of Medicine study, Neriagu reviewed the lives of 30 emperors, from Augustus to Commodus, cross-referencing ancient accounts with modern clinical criteria for lead toxicity. 19 rulers, he found, displayed at least 3 symptoms consistent with high blood lead, ranging from seizures and gout to cognitive decline and sudden mood swings. The case of Caligula stands out. Ancient sources describe a ruler gripped by paranoia, hallucinations, and violent outbursts. Modern neurologists recognize these as classic signs of lead-induced encephalopathy, an unstable mind prone to delusion and aggression. Claudius, remembered for his stammer, tremors, and frequent attacks of gout, fits the profile of chronic Saturnism. The swelling of his feet, the slow speech, the bouts of confusion, each symptom lines up with what physicians now know about lead's effects on the nervous system and joints. Nero's reign offers another example. His biographers noted abdominal pain, erratic sleep, and a persistent metallic taste after meals. He reportedly wore a lead breastplate to strengthen his voice, a detail that in hindsight reads like an unintentional experiment in self-poisoning. Domitian, who reportedly drank only from palace fountains piped with lead and favored sapa-sweetened wine, suffered from chronic headaches, irritability, and progressive paralysis. These are not isolated anecdotes. They form a pattern that echoes across the imperial biographies. Neriagu's analysis does not claim certainty. Ancient texts are colored by politics, and other illnesses may have played a role. But the convergence of symptoms, the timing of Rome's lead peak, and the privileged access of emperors to sapa-laced wine all point toward a hidden vulnerability at the heart of power. In Rome, the very markers of status, abundant wine, elaborate banquets, ornate plumbing, became vectors for a slow, invisible decline. Across the Roman world, access to sapa-sweetened wine was a measure of status, not a universal indulgence. For the elite, wine was not merely a daily drink, it was an essential marker of privilege, consumed in volumes that would stagger modern sensibilities. Literary and archaeological records point to a typical intake of nearly 2 liters per day among senators and wealthy landowners, with sapa stirred into nearly every cup. Banquet manuals describe servers making multiple rounds, refilling goblets with wine laced with syrup, sometimes as often as every course. At the height of Rome's prosperity, a patrician household could go through several amphorae of wine in a single feast, each vessel sweetened to taste. For the urban poor and rural peasants, the story was different. Wine was often watered down, stretched with vinegar, or left unsweetened. Sapa was expensive to produce and required access to both vineyards and metal kettles, resources concentrated in the hands of the wealthy. Public taverns and street vendors rarely offered sapa except during religious festivals or state-sponsored distributions, when the city's authorities provided free cups as a gesture of civic generosity. For most Romans, these occasions were rare. For the privileged, they were routine. This social gradient created an ironic vulnerability. The very people who could afford the finest wine and the richest flavors unwittingly exposed themselves to the highest doses of lead. Modern consumption estimates suggest that an elite Roman might ingest up to 5 milligrams of lead per day from sapa alone, while a plebeian might receive only a fraction of that, often just the background exposure from air and water. The more abundant and frequent the banquets, the greater the cumulative dose. In this way, wealth amplified risk, turning luxury into hazard. As the ice core timeline reveals, the empire-wide surge in atmospheric lead aligns with the period when sapa became a fixture of elite dining, embedding a social divide in both taste and toxic burden. The chemical timeline locked inside Arctic ice does more than echo the rhythms of Roman civilization. It traces them with forensic precision. Each annual band, measured and dated by Joe McConnell's team, reveals how the empire's appetite for metal reshaped the atmosphere. From around 150 BCE, the lead signal climbs steadily, but by the 1st century CE, it explodes, reaching levels more than 30 times higher than any previous baseline. This surge aligns with the documented expansion of Roman mining and smelting, especially in Iberia and the Balkans, where ancient records and archaeological surveys estimate ore processing at a scale unprecedented for the ancient world. To translate these ice-bound concentrations into a picture of real-world emissions, the PNAS study combined archaeological production figures with atmospheric transport models. Using FlexPart simulations and Monte Carlo uncertainty analysis, the team reconstructed how lead plumes would have traveled from Roman mines across Europe and the Mediterranean, riding prevailing winds northward until finally settling into the polar snow. The numbers are staggering. Over the course of the Pax Romana, Roman industry released an estimated 500,000 tons of lead into the air. Each year, up to 1,900 tons drifted beyond the empire's borders, much of it destined for the Arctic. The ice record is so finely resolved that it captures even the disruptions of history. During the Antonine Plague, between 165 and 180 CE, lead concentrations in the cores dropped sharply, mirroring a documented collapse in mining output as the epidemic swept through the workforce. The dip is brief but unmistakable, followed by a return to previous highs as the empire recovers. This synchrony between environmental data and historical chronology closes the loop. The lead peaks in the ice match the zenith of Roman metallurgical activity, while every downturn reflects a crisis recorded in ancient texts. The Arctic, untouched by Rome's armies, preserves a chemical testimony to the scale and the consequences of Roman ambition. Today, the Arctic ice preserves Rome's silent confession, evidence that eluded even Pliny and Vitruvius. The January 2025 study in PNAS, led by Joe McConnell, shows how human ambition can inscribe its own undoing into the planet itself. As modern civilizations generate their own chemical legacies, the Roman lesson endures. What we leave in our environment may judge us long after memory fades. What will future ice remember of us?